Hello everyone, in this lecture we are going to explain atomic nucleus for grade 12 life science and general science. First, nucleus of an atom, composition. The nucleus is constituted of two types of particles. Here is the nucleus. It is composed of protons and neutrons. The protons and the neutrons are both called nucleons. The nucleus of a chemical element is represented by a symbol X, Z, A, where Z is the atomic number of protons, and A is the mass number of nucleons, يعني number of protons and neutrons. N is the number of neutrons. So this is the shape of the atom, model of the atom, which contains protons and neutrons. Around the nucleus, which contains protons and neutrons, there is electrons orbiting around the nucleus. There is a relation between the mass number A and the atomic number Z, such that A equal Z plus N. So A equal to Z plus N. Now we'll talk about isotopes. Isotopes are nuclide of the same element having same atomic number Z but different mass number A. Example, carbon has atomic number 6. So there is two isotopes of carbon here. Both have atomic number 6, but they differ in their mass number. Here the mass number is 12, while in this isotope is 14. Also helium. In helium we have helium, the atomic number is 2, while there is a difference between both isotopes in mass number. Mass number here is 3, while in this isotope is 4. Also we have isotopes of hydrogen. Hydrogen H1 and hydrogen H1 2, hydrogen H1 3, where the atomic number is the same in the three isotopes, but they differ in their mass number. Here is an example. Let's take hydrogen. Hydrogen, there is protium, deuterium, and tritium. H11 has Z equal to 1, H12 has Z equal to 1, H13 has Z equal to 1, but N here is 0, number of neutrons is 0. For H12, number of neutrons is 1. For H13, number of neutrons is 2. So the atomic number is the same, but they differ in their number of neutrons, so in their number in the mass number. Similarly, for the carbon, the atomic number is 6 in the three isotopes, but there is a difference in the number of neutrons, and so in the mass number. In this slide, we are going to explain the dimensions of the nucleus. The nucleus and protons and neutrons have the shape of a sphere. As you can see here, this is the shape of the proton or neutron. It has the shape of a sphere. Also, here is the shape of the nucleus, which has approximately the shape of a sphere. And you know in math that the volume of a sphere equal to 4 over 3 pi r cube. So the volume of proton or a neutron of radius r0 is V0 equal to 4 over 3 pi r0 cube. So the volume of the proton and equal to the volume of the neutron, since they have the same shape and the same volume and radius. The volume of the nucleus is given by V equal to 4 over 3 pi r cube, where r is the radius of the nucleus. Dimensions of the nucleus. If you want to find the volume of the nucleus, you know that the nucleus contains protons and neutrons. So if you want to find the volume of it, you must multiply the number of nucleons that form the nucleus times the volume of the nucleon. So volume of the nucleus equal to A, where A is the mass number of nucleons, times V0, where V0 is the volume of proton or neutron. Then in the previous slide we have seen that volume la nucleus equal to 4/3 pi r cube, while the volume of the proton or neutron is equal to 4/3 pi r 0 cube multiplied by a mass number of nucleons. So you can cancel by 4/3 and pi, you get r cube equal to a r 0 cube. So implies that r equal to a 1/3 r 0, where r0 is a radius of each proton and neutron, v0 is a volume of proton or volume of neutron, r0 equal to 1.2 Fermi. It is constant since the volume of proton and the volume of neutron is constant. So it is equal to 1.2 Fermi. Fermi is a unit where 1 Fermi equal to 1 times 10 to the power minus 15 meter. Approximate mass of the nucleus. The approximate mass of the nucleus denoted by XZA is, since also the nucleus contains protons and neutrons, so the mass of the nucleus depends on the mass of neutrons and the mass of protons. So the mass of the nucleus depends on the number of protons and the mass of protons, also on the mass of protons and the number of protons. So الماس للنيوكليوس, for each nucleus الماس equal Z. Z is the number of protons times the mass of protons, plus N is the number of neutrons times the mass of neutrons. Mass of proton is constant equal to 1.67 when 26 times 10 to the power minus 27 kilogram. It is denoted by 1U, where U is unit of mass. الماس للنيوترون equal to 1.6749 times 10 to the power minus 27 kilogram, and is also equal to 1U, where U is the unit of mass. الM of the nucleus is Z times 1U. 1U is the mass of proton, plus N number of neutrons times mass of one neutron. So mass total equal to Z plus NU, and you know that Z plus N equal to A, so you can say that the mass nucleus is equal to AU, where U is the unit of mass and A is the mass number. Example الماس للهيدروجين 1,3. الماس للهيدروجين 1,3 الهيدروجين 1,3 has a mass number 3, so its mass equal to 3U, and الماس للكربون 612 equal to 12U, since the mass number of carbon is 12. You know that the mass of electron is negligible, so the mass of the nucleus is in general equal to the mass of the atom, since the mass of electron is neglected. The atomic mass unit U, what does it mean? 1U is approximately to 1/12 of the mass of the atom of isotope of carbon. الماس للكربون 612 is equal to 12U, so 1U is equal to 1/12 mass للكربون 612. So 1U is equal to 1.6605 times 10 to the power minus 27 kilogram, and another conversion unit, 1U equal to 931.5 mega electrovolt per C square. Keep in your mind, there is no need to memorize these numbers. In the exam it is given, so there is no need to memorize such constants. Example C612, A mass number is equal to 12 number of nucleons. الماس equal to AU where A is a mass number, so الماس للكربون is equal to 12U, approximate atomic mass. So molar mass equal to mass number A gram per mole equal to 12 gram per mole. This is the approximate mass of carbon. طيب Avogadro's number. Avogadro's number is equal to the number of atoms contained in 12 gram of isotope of carbon, such that Na equal to 6.022 times 10 to the power 23 atoms. يعني every 12 gram of carbon contains 6.022 times 10 to the power 23 atoms of carbon. Approximate density of a nucleus. Nucleus equal mass over volume, where mass is expressed in kilogram, volume is expressed in meter cube, density is expressed in kilogram per meter cube. Okay, so if you want to find the density of a nucleus, mass of nucleus is equal to AU, as you saw in the previous slide. So mass equal to AU, where A is the mass number of the nucleus and U is constant, is equal to 1.6605 times 10 to the power minus 27 kilogram, equal to A times 1.7 times 10 to the power minus 27 kilogram. This is an approximation of U. الفوليوم للنيوكليوس equal to AV0, where A is a mass number and V0 is a volume of each nucleon, equal to A 4 over 3 pi R0 cube. Also this relation we have seen it before. So rho or density is equal to A times 1.7 times 10 to the power minus 27 kilogram mass over الفوليوم A 4 over 3 pi R0 cube. So the rho is, we can cancel here by A, so we get a constant number. So the rho of the nucleus or density of the nucleus is independent on the mass number. So rho is constant and it is independent of the mass number. All nuclei have the same density. So for this number, this density is the same for all the nucleus in the world. Since as you see here, the density is independent on the mass number A. Mass defect. The mass of the nucleus of helium He24 is 4.0015 U. This is the mass of a helium nucleus. But they noticed that the mass of its 4 nucleons, you know that the helium is composed of 4 nucleons, 2 protons and 2 neutrons. So the mass of each of 2 protons and 2 neutrons, the sum of their masses is equal to 4.03188 U, which is more than that of the mass of the nucleus of helium. So as you see here in the picture, mass of helium is less than that of its constituents. So there is a mass defect. There is a mass defect. Where is this mass? So the mass of the nucleus is less than the sum of its different nucleons taken separately. So mass of helium alone is less than that of the mass of its constituents, which are 2 protons and 2 neutrons. So as a conclusion, we noticed that the mass of any nucleus is less than the sum of the masses of its constituents. So let's denote by mass of nucleus by mx, where x is a symbol of the nucleus. The difference delta m between the sum of masses of the nucleons taken separately and the mass of the nucleus is called mass defect. So there is a mass defect such that delta m, the mass defect, this mass defect equal to Z mass للبروتون plus A minus Z mass للنيوترون minus mx. يعني الدلتا M الماس defect equal to الماس للconstituents forming the nucleus minus الماس للnucleus. In the next slide, we will talk more about this mass defect and we will learn how it will appear in binding energy. Binding energy, energy needed to decompose a nucleus into its nucleons. So, the mass defect that we have explained it, delta M equal Z mass proton plus N mass neutron minus mx. And this is very important rule that the mass is converted into energy. Okay, so according to Einstein, this mass defect changes into an energy that bonds the nucleons together. It is called binding energy. So the mass defect that we have talked about it appears as energy, and we can find this energy by this relation E binding energy equal to mass defect multiplied by c square. So binding energy equal mass defect multiplied by c square, where the binding energy is in joule and delta M mass defect is in kilogram and the c is in meter per second. Another units we can use it. If you use the unit of mass mega electrovolt per c square and use c square, so you will get here the unit of energy mega electrovolt. In this slide, we'll talk about interaction within the nucleus and its stability. Nuclei are classified into two types, stable nuclei and unstable nuclei. Stable nuclei where the number of nucleons is stable and doesn't change. Example, hydrogen and carbon, they are stable nuclei. While unstable nuclei are those where the number of nucleons changes and varies naturally, spontaneously. Example, uranium and plutonium, where these two nuclei disintegrate and transformed into other nuclei, or loses some of their neutrons or protons. Binding energy per nucleon. Binding energy per nucleon measures the stability of a nucleus. So, the binding energy that binds the nucleons to each other, it measures the stability of the nucleus. Binding energy per nucleon ratio, it is the ratio of the binding energy to the number of nucleons in the nucleus. So it is binding energy per nucleon is equal to binding energy over mass number. The more stable nucleus is one having more binding energy. So when the binding energy per nucleon increased, so it becomes more stable. As B over A increases, stability increases. So if binding energy per nucleon of a nucleus X is more than that of a nucleus Y, then X is more stable than Y. In this slide, we'll take another example. Consider two nuclei, 1 and 2, where the mass number of nucleus 1 is A1 and the mass number of nucleus 2 is A2. Binding energy per nucleon for nucleus 1 is 7 mega electrovolt per nucleon, while for the binding energy per nucleon for nucleus 2 is 8 mega electrovolt per nucleon. You notice that the binding energy per nucleon for nucleus 2 is more than that of nucleus 1, so 2 is more stable. So you can notice that 2 is more stable than 1. Stability of the nucleus. A nucleus is said to be stable if it is not subjected to any spontaneous decay or transformation. Yani it doesn't change into another nucleus or it doesn't make any disintegration. So it is stable. The greater the energy needed to break a nucleus into its individual nucleons, the more stable it is. So if it is hard to break the nucleus, so it is stable, it's more stable. The binding energy of a nucleus is not the same for all nuclei. Of course, every nucleus have a certain binding energy for it. A nucleide is more stable than another if the binding energy per nucleon of the first is greater than that of the other. In this slide, we will talk about the curves that describes the binding energy of a nucleus as function of the mass number. Here is the Aston's curve. Aston's curve here, you can see the mass number of the nuclei here on the abscissa, and on the ordinate you can see the binding energy per nucleon. So this curve represents the binding energy per nucleon as function of the mass number. So Aston's curve represents the variation of the binding energy as a function of the mass number A. You can notice that between mass number 0 and 20, the binding energy is less than 8 mega electrovolt, while when the mass number is between 20, as you see, 20 and 190, here 190, you see that the binding energy per nucleon is more than 8 mega electrovolt, while it starts decreasing after 190, after A equal to 190, such that for A greater than 190, the binding energy per nucleon is less than 8 mega electrovolt. So you can deduce that the nuclei that have mass number between 20 and 190 is more stable, since the binding energy per nucleon is greater than 8 mega electrovolt. Interactions within the nucleus. Being all positively charged, protons of the nucleus mutually repel each other, which tends to break the nucleus. You know that protons are positively charged, so there is a force of repulsion inside the nucleus between the protons, and the neutrons have no charge, so they don't exert any electrostatic interaction. But also you know that the nucleus combined with a very strong force, the nucleus does not explode. The nucleus does not explode by the effect of the forces of repulsion between the protons. So there should be a new unknown kind of forces that attract the nucleons to each other. These forces are called strong interactions. Most nuclei having mass number between 20 and 190 contain more neutrons than protons, and this is the cause of their stability, because the attractions, strong interaction, are greater than the repulsion. So if A mass number is greater than 190, the nucleus becomes unstable because it becomes large in size, and the nucleons become far from each other, and the strong interaction becomes less effective.